Beneath the tangled roots of the Amazon rainforest, where the earth breathes in slow rhythms and light filters down through a cathedral of leaves, there exists a world few ever see. It is a world of darkness, moisture, and endless decay. Yet within that decay, life thrives with extraordinary complexity. The soil is alive, an unseen metropolis humming beneath our every step. To most, the ground is simply ground, a surface to walk upon. But to those who study the deep history of life, it is an archive. Every grain of soil holds stories, not of years or centuries, but of epochs. It is in these forgotten depths that one of the oldest lineages of life still stirs, silent and unnoticed. Creatures no larger than a grain of rice move through narrow tunnels and chambers carved by generations of ancestors. They are the architects of the earth, builders, farmers, and soldiers, a civilization hidden beneath our feet. And among them lies a lineage that began before mammals had even risen to dominance, before birds had filled the skies, before flowers had colored the land. This is where our story begins. Not with humans, not even with dinosaurs, but with an insect so ancient and elusive that its discovery rewrote the story of life itself. It begins with Martialis Heureka, a creature so strange, so unlike any other ant known to science, that it was called the ant from Mars. Long before its name was spoken aloud in laboratories or written into taxonomic charts, the world it came from was already ancient. Picture the Amazon basin today, vast, humid, and teeming with life. But imagine it stripped of the sounds of birds and mammals. Imagine no human voices, no axes, no engines, only the eternal sound of rain falling on leaves. That endless rain has always been here, long before our kind walked upright. The same rain nourished forests that have risen and fallen for over 100 million years. And beneath those forests, in the deep, loamy soil, life was quietly conducting its own experiment. Small, eyeless creatures tunneled in silence, evolving strategies that would one day dominate the earth. The modern Amazon is more than a forest, it is a living time capsule. Each layer of soil contains echoes of the distant past. Every fallen leaf adds to a tapestry woven over millions of years. When we walk upon it, we are treading on the surface of time itself, a stratified history of life. But for most of history, humanity has looked outward, to the stars, to mountains, to oceans. Few thought to look down, beneath the very soil that sustains us. It took centuries of observation, collection, and microscopic study before we began to understand that some of the most profound mysteries of evolution lay not in fossils embedded in rock, but in the living creatures crawling underfoot. Ants are among the most successful organisms on Earth today. There are more than 14,000 known species, and for every human on the planet, there are estimated to be 1 million ants. They live on every continent except Antarctica, inhabiting deserts, rainforests, mountaintops, and city pavements. Their societies are complex, their cooperation unrivaled. But for all their ubiquity, their origins were once shrouded in mystery. Scientists knew that ants had evolved from wasp-like ancestors sometime during the age of dinosaurs, but the fossil record remained frustratingly silent. The earliest known ants, preserved in amber, dated back to roughly 100 million years ago, already advanced, already diversified. But what came before them? What did the first ants look like? Where did the lineage begin? For decades, these questions remained unanswered. Researchers theorized, compared, and speculated, but no definitive proof emerged. The earliest roots of the ant family tree seem to have been lost to time. That is, until a specimen no larger than a few millimeters was discovered in one of the most biodiverse regions on Earth. In 2003, deep in the Brazilian Amazon near the city of Manaus, an entomologist and his team sifted through the thick, moist litter of the forest floor. Their work was meticulous and patient, the kind of science that rewards persistence rather than luck. As they separated grains of soil and fragments of leaves, they noticed something unusual. A pale, slender insect unlike any they had seen before. It was ant-like, yes, but also distinctly alien. It lacked eyes. Its body was smooth and pale, almost translucent. Its mandibles, the jaws used for gripping and cutting, were elongated, curved like delicate scythes. Its movement was slow, deliberate, almost ghost-like. The team collected the specimen carefully, uncertain of what they had found. It was labeled, preserved, and set aside for study. At the time, it did not appear to be a groundbreaking discovery. But years later, under the scrutiny of more detailed analysis, its true identity would emerge, and with it, a revelation that would send ripples through evolutionary biology. To understand why Martialis Heureka is so important, one must understand what ants represent. They are not just insects, they are an evolutionary triumph. From small, solitary ancestors, ants evolved complex social systems that rival the organization of human civilizations. Within their colonies, individuals perform specific roles: workers, soldiers, queens, and males. Communication is achieved through a sophisticated language of chemicals, pheromones, that convey everything from alarm signals to navigation cues. Their ability to cooperate allows them to achieve feats of engineering and warfare unimaginable for creatures of their size. Some species cultivate fungus gardens, others herd aphids as livestock. Some wage wars on neighboring colonies, others act as scavengers, cleaning the ecosystem. Together, they form superorganisms, colonies where the individual exists only to serve the collective. But none of this complexity appeared overnight. It began somewhere, with a single evolutionary experiment that succeeded. The first ants were likely solitary hunters, their social behavior emerging gradually as an adaptation for survival. And Martialis Heureka, as genetic studies suggest, may be the closest living relative of that original lineage. The name Martialis Heureka tells a story in itself. Martialis, from Latin, means of Mars, a nod to its strange, otherworldly appearance. Heureka is Greek for "I have found it," the famous exclamation attributed to Archimedes upon making a discovery. Together, the name reflects both its alien form and the excitement it brought to science. When molecular studies were conducted, researchers were astonished. The DNA sequences of Martialis did not neatly fit within any existing subfamily of ants. Instead, they branched off near the very base of the ant evolutionary tree. This meant that Martialis was not just a new species. It was a window into the earliest history of ants, a living representative of a lineage that diverged over 100 million years ago. This discovery was nothing short of revolutionary. For the first time, scientists could glimpse the features of what the earliest ants might have looked like: eyeless, subterranean, and predatory. In the grand timeline of life on Earth, such moments of revelation are rare. Fossils often tell us stories in fragments, but living species like Martialis offer something different: a bridge between past and present, a thread of continuity that stretches across deep time. Imagine for a moment that you could stand in the Cretaceous forest, 120 million years ago. The air would be thick with humidity, heavy with the scent of resin and decay. Giant cycads and ferns dominated the landscape. Primitive flowering plants were only beginning to bloom. The buzz of ancient insects filled the air, and somewhere in the shadows, a small, pale creature crept through the soil, unseen by the giant reptiles that ruled above. It is humbling to think that the descendants of such a creature now dominate the planet in ways those ancient giants never could. Yet for all its importance, Martialis Heureka remains one of the rarest creatures ever found. Only a handful of specimens have ever been collected. It lives underground, away from light, in the damp soil of one of the most complex ecosystems on Earth. It does not seek attention. It has survived countless changes in climate, geography, and biology. Silently, persistently, as the world transformed around it. To hold such a creature in one's hand is to hold history itself. Not the history written in books, but the kind that predates words, the history written in genes, in form, in instinct. The forgotten world beneath our feet is not a relic of the past. It is alive. It continues to evolve, to adapt, to whisper the same story it has told for hundreds of millions of years, the story of life's resilience and its unending capacity to endure. And as we look down, perhaps we begin to realize that the greatest mysteries of evolution were never hidden in the stars above us, but in the soil below. The clock of the Earth winds backward, millions of years retreating like waves pulling away from a shoreline of time. The continents shift, oceans shrink and swell, and the face of the planet becomes almost unrecognizable. The world of the Cretaceous period dawns, an age of giants, of heat, of flourishing life unlike any that came before. 120 million years ago, the Earth was warmer, humid, green, and restless. The poles were free of ice, and the sea levels were high, swallowing coastlines and flooding vast regions into shallow inland seas. The air shimmered with moisture, thick with the scent of resin, pollen, and life. The planet was in full bloom, yet it was also a world in transition, a crossroads between ancient life and the dawn of the modern world. It was the time of the dinosaurs, yes, but it was also the time of the first flowering plants, the first birds, the first whispers of the ecosystems we know today. And beneath the towering forms of sauropods and tyrannosaurs, in the unseen soil of prehistoric forests, something smaller and far more enduring was beginning to emerge. Imagine standing in a Cretaceous forest. The light falls in golden shafts through the canopy of cycads and conifers. Primitive magnolias and laurels bloom in quiet defiance beneath the shade. Ferns stretch outward like green lace over the damp earth. Somewhere in the distance, the rhythmic croak of early frogs echoes beside a slow-moving stream. Beetles crawl through rotting wood, dragonflies dart through misty air, and early wasps flit between the flowers of newly evolved angiosperms. Beneath your feet, the soil teems with unseen life. Mites, larvae, centipedes, and something else, a lineage of small, pale insects experimenting with something entirely new in nature, cooperation. This was the beginning of an empire that would outlast the dinosaurs themselves. The Cretaceous was a time of innovation. Evolution was not hurried, but it was relentless. Each niche, each microenvironment, was being filled by life adapting to survive. Insects were at the forefront of this transformation. While the reptiles ruled above, the insects conquered every hidden layer below, in wood, in leaf litter, and in soil. Among them were the early members of a group known as the Vespidae, wasps. Agile predators, efficient hunters, they were the ancestors of both bees and ants. They hunted small arthropods, paralyzing them with venom, and laying their eggs inside their prey, an efficient, if macabre, system of survival. But somewhere among these solitary wasps, a mutation took hold, a shift in instinct, subtle but revolutionary. Some began to remain near their nests after the offspring emerged. Some began to share food. Some began to communicate. In that moment, however imperceptible, cooperation became as valuable as competition. And evolution took notice. The earliest ants were born from this quiet transformation. They retained the wasp's body structure, a narrow waist, powerful mandibles, and a stinger, but their behavior was changing. They began to live not as individuals, but as collectives. The survival of one depended on the survival of all. Over millions of years, this small behavioral shift would give rise to one of the most successful forms of life ever to walk the earth. Yet the evidence of their origin is almost invisible. Ants are delicate, their bodies fragile, easily destroyed by the passage of time. The fossil record of such creatures is rarely generous. While the bones of dinosaurs fossilized in rock, the bodies of ants disintegrated into dust long before the next geological layer settled upon them. For decades, paleontologists searched for the earliest ants, the missing link between solitary wasps and social superorganisms. Amber, fossilized tree resin, became their window into that world. Within droplets of ancient resin, trapped and preserved for eternity, scientists found glimpses of life frozen in motion. The curve of a mandible, the delicate line of an antenna, a leg mid-step. These amber fossils from the late Cretaceous revealed ants already well adapted, with complex body structures and specialized casts. It was clear that by 100 million years ago, Ants were already diverse. But when had they begun? What lay before these amber relics? That question lingered like a whisper from the Cretaceous. To imagine that first ant, one must peel back layers of time and consider the Earth as it was, an unstable, dynamic, creative system. Continents were drifting apart. South America and Africa had only recently separated, their rift giving birth to the early Atlantic Ocean. Volcanic activity was rampant. The skies were heavy with carbon dioxide, trapping warmth across the globe. And within that warmth, evolution thrived. Forests grew in thick bands from equator to pole. Rivers meandered through deltas rich in organic life. Swamps buzzed with insects that had perfected flight. Early mammals, still small and secretive, scurried through the undergrowth, avoiding the watchful eyes of reptilian predators. In this teeming environment, the small mattered as much as the large. Each leaf was a continent, each drop of resin a sea. It was here, in the shadows of towering cycads, that ants began their silent conquest, not with teeth and claws, but with unity. The transition from wasp to ant likely occurred in the dark. Unlike their airborne ancestors, the first ants abandoned the sky for the soil. They traded speed for secrecy, light for safety. Living underground protected them from predators and climatic extremes, but it came with a cost, the loss of sight. In the absence of light, eyes became unnecessary. Chemical communication took over where vision ended. Smell became their map, touch became their language. In this hidden world, the foundations of ant society took root. Imagine one of these early ants, pale, eyeless, moving slowly through a tunnel of compacted soil. Its antennae sweep the air in rhythmic arcs, reading invisible signals. It senses its kin nearby, faint traces of pheromones marking a shared path. It encounters another ant, brushes antennae against antennae, and a message passes between them, of food, of danger, of direction. In this silent, tactile dialogue, the first social bonds of the ant world are formed. This subterranean strategy was so successful that it has barely changed in over 100 million years. The modern Martialis Heureka, found deep within the Amazon soil, lives almost exactly as its ancestors did during the Cretaceous. If one could travel through time, descending through the ancient layers of Earth, one might watch as this evolutionary experiment unfolded. Over millions of years, the ant's anatomy refined itself to perfection. Its waist became narrower, allowing flexibility and movement in tight spaces. Its jaws became tools of both war and construction. Its antennae grew longer and more sensitive. The stinger, once a weapon of solitary defense, became an instrument of collective purpose. Every detail was honed by the pressures of survival, not for the individual, but for the colony. Ants evolved not as singular beings, but as parts of a greater organism. In evolutionary terms, this was revolutionary. Natural selection acting not only on individuals, but on societies. The Cretaceous world, though lush, was perilous. Fires swept through forests. Volcanic ash darkened skies. Meteor impacts scarred the surface of the planet. Species rose and vanished in the blink of geological time. Yet the lineage that would become the ants endured, hidden and resilient. Their survival was not guaranteed by strength or speed, but by cooperation. And so, while dinosaurs thundered across plains and reptiles ruled the skies, a quieter dynasty began, one that would outlast them all. In time, as continents drifted and climates shifted, the descendants of those early ants spread. They diversified, adapted, and conquered every ecological niche imaginable. But that story comes later. For now, in this chapter of Deep Time, the ants were still whispers, faint, subterranean, and unseen. Their societies existed beneath the roots of primeval trees, under the fallen leaves of ancient forests. No light reached them, yet they thrived in silence. Theirs was a story that would remain buried for over 100 million years, until the discovery of Martialis Heureka gave it a voice once more. When scientists unearthed the pale, blind ant in the Amazon soil, they weren't merely finding a new species. They were uncovering a survivor from the Cretaceous, a being that had persisted almost unchanged while empires rose and fell, while mountains formed and eroded, while ice ages came and went. The whisper from the Cretaceous had finally become a voice. And it spoke of patience, of persistence, of life that refuses to vanish. In the great narrative of evolution, few creatures can claim such endurance. The dawn of the ant empire began in silence, beneath the soil, within chambers of darkness that the sun has never touched. It did not begin with a roar of conquest or a surge of predators, but with something smaller, subtler: cooperation. In the grand story of life, there are moments when survival shifts its strategy. For hundreds of millions of years, evolution had favored the strong, the swift, the solitary. But in the shadows of the Cretaceous forest, another rule began to take shape, a rule that would one day reshape ecosystems across the world. The rule was simple: together, we endure. As the world above pulsed with dinosaurs and flowering plants, the underground realm was awakening with a quieter revolution. The early ants, pale, delicate descendants of wasp-like ancestors, began to master the art of unity. What began as a few cooperative gestures between individuals slowly crystallized into structure. The sharing of food, the guarding of larvae, the defense of a common nest. Small behaviors, repeated and perfected over generations, built a foundation far stronger than any exoskeleton. Each ant was small, fragile, almost insignificant on its own. But within the colony, the sum became greater than its parts. The colony was no longer just a group of individuals. It was an organism, with its own heartbeat, rhythm, and purpose. This was the true birth of the ant empire, not a conquest of territory, but a conquest of behavior. To understand the magnitude of this transformation, we must look closely at what it means to be social in the insect world. The first step in social evolution is called eusociality, a rare and complex form of organization that only a handful of creatures have ever achieved. It is defined by three main traits: cooperative brood care, overlapping generations within a colony, and a division of labor between reproductive and non-reproductive individuals. In simpler terms, it means that some individuals in a species willingly give up their own chance to reproduce in order to help others, usually a queen, raise offspring. It is, by all definitions of nature's struggle for survival, a paradox. Why would evolution favor those who do not pass on their genes directly? And yet, in ants, bees, termites, and a few other lineages, this selflessness became the key to domination. In the world of early ants, these changes began gradually. A single female, descended from solitary hunting wasps, might have nested in a patch of soil or decaying wood. Instead of abandoning her offspring after laying eggs, she remained to guard them, to feed them. Perhaps one or two of her daughters, upon maturing, stayed behind to help her instead of dispersing. Over time, this instinct solidified into a behavioral blueprint. The queen became the mother of the colony. Her daughters, the workers, became her hands and eyes. They hunted, they built, they fed her young. In doing so, they ensured not only her survival, but their own genetic legacy. For in aiding the queen, they were preserving a portion of themselves. This cooperative structure, simple at first, became increasingly specialized. Workers evolved smaller bodies, better suited for labor. Soldiers grew larger mandibles for defense. The queen, freed from all duties except egg-laying, became the heart of the colony, a living engine of reproduction. Thus, the first societies were born not in the open air but in the quiet of the soil, where life is measured not by noise or spectacle, but by persistence. The Cretaceous world was still ruled by giants, but the ants were quietly multiplying. Their nests became fortresses of communication, entire civilizations conducted through touch and scent. Ants do not speak, nor do they see as we do. Their world is a symphony of chemicals. Through pheromones, they convey messages of astonishing complexity. A single ant can mark a trail to food, warn of danger, or signal victory. Each chemical cue is a word, each combination a sentence, each colony a living library of sense. This chemical language became the cornerstone of their empire. It allowed coordination on scales unmatched by any solitary creature. Hundreds, even thousands of individuals could act in unison, responding as though driven by one collective mind. In time, this unity would enable them to build vast underground networks, wage wars, enslave other species, and cultivate their own food. But in the beginning, it served a simpler, nobler purpose: survival. It is difficult for us, as large creatures, to comprehend the significance of this transformation. We are drawn to the grand and the visible, the dinosaurs that towered above forests, the pterosaurs that spanned the skies. Yet the future of Earth's ecosystems was being written by beings smaller than a raindrop. The rise of ants was not explosive. It was patient, deliberate, evolutionary. Like roots spreading quietly beneath a tree, their influence grew unseen until one day, it was everywhere. While the great reptiles faced extinction, while continents drifted apart and climates changed, the ants adapted. Their strength lay in flexibility, in numbers, and in cooperation. Each colony could move, rebuild, and multiply with astonishing efficiency. The fall of one nest meant little when 1,000 more thrived nearby. In evolutionary terms, they had discovered immortality. Not for individuals, but for the collective. The world was changing around them. As flowering plants spread, so too did insects that fed on nectar and pollen. Forests became more diverse, ecosystems more interlinked. The ants, ever adaptable, evolved to fill new roles: scavengers, predators, seed dispersers, even farmers of fungus. Each adaptation built upon the last. Their mandibles diversified. Some became sharp for hunting, others broad for carrying. Their body sizes split into castes. Some grew massive heads to block nest entrances. Others shrank, slipping through the smallest crevices. The ant empire was diversifying, an invisible kingdom beneath the feet of dinosaurs. And yet, for all this innovation, there was still one mystery: their origin. The ants had already begun to radiate into many forms by the late Cretaceous, as shown by amber fossils discovered millions of years later. But the ancestral stock, the first lineage, remained elusive. It would not be until over 100 million years later, in the heart of the Amazon rainforest, that a living descendant of that primal form would be found. Pale, eyeless, a ghost from deep time. Martialis Heureka would become the key to unlocking how those early societies looked, behaved, and survived. But before that rediscovery, the ants continued their slow, silent conquest. By the end of the Cretaceous, the ant empire was firmly rooted. Colonies dotted the forest floor, hidden beneath moss and decaying logs. When the mass extinction event struck, when meteors fell and darkness swept the earth, the dinosaurs vanished, but the ants endured. Their underground homes insulated them from the firestorms and climate collapse that followed. Their flexible diets allowed them to survive when others starved. Their reproductive systems ensured rapid recovery once conditions stabilized. It was perhaps the greatest evolutionary insurance policy ever devised. When the earth healed, the ants emerged unchanged, still organized, still united, still quietly building. The world they inherited was emptier, but full of opportunity. And so, from the ashes of the dinosaurs, the age of mammals began, and alongside it, the silent continuation of the age of ants. The birth of the ant empire was not marked by a single moment or event. It was an accumulation of small triumphs: the refinement of behavior, the perfection of structure, the mastery of cooperation. Each nest, each generation, each evolutionary step contributed to a legacy that would come to shape the planet's ecosystems. From rainforests to deserts, from mountain slopes to city streets, the blueprint of Martialis and its kin would spread across every continent. In time, their presence would become so common that we would cease to notice them. Yet beneath the surface of our daily lives, their empire continues, patient, tireless, and vast. They are the engineers of the soil, the unseen governors of ecological balance. Every handful of earth is their domain, every fallen leaf a resource, every grain of sand a frontier. And it all began in that ancient, shadowed world, with the first whisper of unity beneath the Cretaceous sun. The ants were born in darkness, but their influence would come to touch everything under the light. For every species that ever lived, the earth keeps a record, but it is a record written in fragments, scattered and incomplete. Fossils are the syllables of this ancient language, but time erases most of what is written. Only the rarest of circumstances, the precise alignment of chemistry, pressure, and patience, can preserve a trace of life long after the living world has moved on. And so, for creatures as small and fragile as ants, the silence in the stone record is profound. For millions upon millions of years, their existence was hidden from us. We walked the earth unaware that beneath our feet, an empire older than humanity thrived. It was only through the faintest whispers, a mandible trapped in amber, a shadow in shale, that the early story of ants began to re-emerge from the void. The irony of the ants' history is this. While they came to dominate the earth, their beginnings left almost no trace. Bones fossilize, chitin rarely does. Large animals leave behind skeletons, footprints, and shells. Ants, built from soft, delicate exoskeletons, vanish into dust the moment decay begins. Even when their bodies fall into mud or resin, the odds of preservation are vanishingly small. For paleontologists, reconstructing the early history of ants has been like listening to an orchestra in which 99 out of 100 instruments are silent. The melody is broken, the harmony incomplete, yet within those faint surviving notes lies the shape of something extraordinary. In the 19th century, as naturalists began cataloging the world's insects, they found themselves haunted by a mystery. Ants were clearly ancient. Their diversity, complexity, and global spread suggested a lineage stretching deep into geological time. But the oldest known fossils were disappointingly recent. Specimens discovered in Baltic amber dated back only about 40 million years. These were already highly specialized, fully social ants, not primitive at all. Later, in the 20th century, new finds pushed that date back further, to roughly 100 million years. Ants preserved in Burmese and New Jersey amber revealed creatures that lived alongside dinosaurs. Yet even these were advanced in structure, belonging to families that still exist today. Where, then, were the ancestors? If these ants were already complex and widespread during the age of dinosaurs, their origin had to lie far deeper in time, perhaps 120 or even 150 million years ago. But no fossils had survived to tell that story. It was as if the first chapters of their evolution had been erased. Scientists often call such gaps in the fossil record ghost lineages, the unseen stretches of evolutionary history inferred by genetics, but missing from stone. Ants have one of the longest ghost lineages known. Molecular studies show they diverged from their wasp ancestors in the early Cretaceous, yet the physical evidence for that divergence remained invisible. The challenge, of course, lies not only in preservation but in discovery. Fossils are found where sedimentation occurs, in rivers, lakes, or volcanic ash beds. Ants live underground or in wood, habitats rarely conducive to fossilization. When they die, their bodies decompose quickly, their history lost in the cycle of decay. The only reason we know anything about ancient ants at all is because some were trapped in resin, sticky tree sap that oozed down bark and hardened over time, creating nature's own time capsules. Amber is the great preserver of small lives. It captures not bones but moments, an insect mid-flight, a leaf mid-fall, a raindrop frozen in descent. Each piece is a window into a vanished world. Through amber, we have seen ants walking across the surface of Cretaceous trees, frozen in motion as if unaware that eternity had just begun around them. But amber can only tell part of the story. It preserves the creatures that lived above ground, those that walked on bark, foraged on the forest floor, or climbed into the light. The early subterranean ants, the ones that dug and hid, remained out of reach. Their world, the soil world, is one of endless recycling. Organic matter decomposes, compresses, dissolves, and reforms. Little remains intact long enough to fossilize. In this environment, even the greatest evolutionary transitions can pass unnoticed. For decades, entomologists combed through amber deposits across the globe, from Myanmar to New Jersey, from Lebanon to France, hoping to find something, anything, that might represent the earliest stages of ant evolution. They found variety, yes, species with wings, with spines, with mandibles shaped like traps, but not the ancestral form. The silence continued. To many, this silence was frustrating but familiar. The fossil record of insects is always a patchwork, a puzzle with more empty space than pieces. Yet for scientists seeking the roots of ant evolution, it became almost personal, a quest to find the origin of one of Earth's most successful creatures. In the 1980s and 1990s, advances in genetic analysis offered new clues. By comparing DNA sequences between living ants, researchers could estimate when their common ancestors diverged. These molecular clocks pointed to a date far older than the amber fossils suggested, around 120 to 140 million years ago. That meant that for at least 20 million years, ants had existed without leaving a single fossil trace. It was a void in both rock and understanding. But in science, silence is never truly empty. Each unanswered question becomes a force that pulls inquiry forward. The absence of fossils only deepened the determination to find them. Teams began exploring new regions, not only for fossils but for living species that might carry ancestral traits. They looked to the tropics, to the ancient rainforests where evolution's experiments have always persisted the longest. If the earliest ants had survived in any form, it would be there, in the dark, humid soils of the world's oldest ecosystems. Researchers began to realize that the answers might not lie entombed in amber or rock, but in living insects that had changed little over time. Evolution does not always erase the past. Sometimes, it preserves it in living form. The concept of living fossils has long fascinated biologists, organisms that appear almost unchanged over immense stretches of geological time. The coelacanth, the horseshoe crab, the tuatara, all examples of species that defied extinction and remained as echoes of ancient life. Perhaps, some scientists reasoned, the ancestral ants had done the same. Perhaps they still moved unseen beneath the forest floor, their lineage unbroken since the Cretaceous. It was a tantalizing thought, and one that would soon be vindicated. But before that breakthrough, the search was marked by frustration and false leads. Specimens were misclassified, fossils misinterpreted. Some insects found in amber were thought to be proto-ants, only for later studies to reveal them as unrelated wasps. Each discovery sparked brief excitement, followed by quiet disappointment. The fossil record remained stubbornly incomplete. The ants' early story was still missing, buried not in rock, but in time itself. And yet, even in that silence, there was meaning. The absence of fossils told its own story, of creatures that lived where fossils rarely form, of lives conducted in darkness rather than light. In that sense, the missing fossils were not evidence of failure, but of success. They testified to a lineage that had adapted perfectly to environments that left no record, a hidden triumph beneath the geological silence. When we think of the fossil record, we often imagine great skeletons, bones of giants displayed in museum halls. But the history of life is not measured by the colossal alone. The most important transitions, the ones that shaped ecosystems and evolution, are often invisible. The birth of social behavior, the emergence of cooperation, the rise of complex communication. These left no bones, no tracks, no fossils. They live only in the descendants that inherited those instincts. And so, while paleontologists searched for ancient ants in stone, the true fossils, living fossils, continued their quiet work beneath the forests of the modern world. Among them, deep in the Amazon, was Martialis Heureka, the creature that would one day break the silence. In hindsight, the long absence of fossils makes sense. The earliest ants were blind, subterranean, and rare. They did not venture into the resinous world of trees where amber could preserve them. They lived and died in the shadows of the soil, their remains consumed by the same processes that sustained their colonies. It was this very invisibility that allowed them to endure. Theirs was not a history written in stone, but in continuity, a line unbroken by disaster, shielded by the earth itself. And so, when scientists finally found Martialis Heureka in the 21st century, it was not just a discovery of a new species. It was the end of a silence that had lasted 100 million years. A whisper, once lost in the depths of time, had at last been heard. It began with a handful of soil. Deep in the heart of the Amazon rainforest, where sunlight falls in green-gold shafts and the air hums with unseen life, a quiet revolution was waiting beneath the leaves. For centuries, the forest had concealed secrets older than itself, remnants of worlds that had vanished before mammals had even risen. The soil here is more than earth. It is a living archive. Each grain carries the dust of ages, the remains of forgotten species, and the whispers of evolution's earliest experiments. It was in this living archive that one of the most extraordinary discoveries of modern biology would be made. In 2000, the Brazilian biologist Dr. Christian Rabeling and his colleagues were exploring the leaf litter and soils near Manaus, a city at the heart of the Amazon basin. Their goal was not glory, but taxonomy, the patient, meticulous work of cataloging life, one specimen at a time. Armed with tweezers, magnifying lenses, and a deep reverence for the hidden world beneath their boots, they sifted through the forest floor, a place where sunlight rarely touches, but where life is most abundant. Most of what they found was familiar to an entomologist. Tiny beetles, mites, soil-dwelling ants, fragments of roots. But one day, in a small vial of collected soil, Rabeling noticed something that didn't belong. A pale, slender insect, almost ghost-like, floated among the debris. It was an ant, yes, but not like any ant he had ever seen. Under the microscope, the creature seemed to defy classification. Its body was elongated, serpent-like, its legs delicate and spidery. It had no eyes. Its antennae were long, almost whip-like, sweeping the air as if feeling the unseen world around it. Its mandibles curved sharply inward, not for cutting or grinding, but for grasping, precise, surgical instruments from another time. And its color, a translucent milky white, made it look more like a spirit than a living insect. In that moment, Rabeling realized he might be looking at something extraordinary. Not a new species merely, but a new window into the past. He collected the specimen carefully, preserving it for further study. Over the following years, he and his collaborators analyzed its anatomy, compared it to known ant families, and searched for others like it. They found only a few. All from deep soil layers. All blind. All sharing the same ghostly appearance. And when they ran the DNA tests, the results astonished them. This was not just another species. It belonged to a lineage entirely separate from every known ant family, a lineage that branched off near the very base of the ant family tree. In evolutionary terms, it was like finding a living relative of the first humans. They named it Martialis Heureka, Latin for from Mars and discovery. The name reflected both its alien appearance and the sense of astonishment it inspired. Heureka, I have found it. It was, quite literally, the discovery of a lifetime. When news of Martialis broke in 2008, the scientific community responded with both awe and disbelief. For over a century, researchers had sought the missing link between modern ants and their wasp-like ancestors. Now, in the damp soil of the Amazon, that link had crawled into the light. Martialis Heureka was primitive in almost every sense, blind, subterranean, and solitary. It had the basic body plan of an ancient insect, yet it was clearly an ant. Its genetic signature placed it right at the root of the Formicidae family tree, older than any living antline. It was not just a new species, it was a living fossil. What made Martialis so fascinating was how much it didn't have. It lacked the advanced features of modern ants. No complex eyes, no specialized body armor, no visible stingers. It seemed stripped down to the essentials, as if evolution had frozen it midway through transformation. Yet it was perfectly adapted to its world, the soil. Its long, sensitive antennae were its eyes. Its pale body was suited for darkness. Its slender limbs moved easily through narrow tunnels. It was not primitive in the sense of being unfinished. It was ancient and complete in its own right, shaped by an environment unchanged for millions of years. Martialis did not evolve for the light. It evolved for the silence beneath. The implications of its discovery were profound. For the first time, scientists could glimpse what the earliest ants might have looked like. Small, blind, and subterranean, descended from solitary wasps that had abandoned the surface world for the shelter of the soil. It confirmed what many had long suspected, that ant evolution began underground, not in the open. The first ants were creatures of darkness, living in the safety of the earth while dinosaurs thundered above. And from these humble beginnings, the great social empires of ants would rise. In Martialis, the ancient blueprint was preserved, a fossil not of stone, but of DNA. To study Martialis is to peer into deep time without leaving the present. Every detail of its anatomy is a message from the Cretaceous, a whisper from the dawn of social life. Its mandibles, thin and curved, suggest a predatory habit, perhaps feeding on soft-bodied prey like other soil arthropods. Its lack of eyes points to a life spent entirely in darkness. Its smooth, pale body indicates it rarely, if ever, ventured to the surface. But most revealing is its solitary nature. Unlike modern ants, Martialis does not appear to live in large colonies. It is a shadow of what ants once were, a step before full eusociality took hold. In it, we see the transition, the moment when cooperation was still a fragile experiment, when individuality had not yet been fully surrendered to the collective. Finding Martialis Heureka was not just a scientific triumph, it was a humbling reminder of how much remains hidden. For every species that has been named, countless others still move unseen beneath our feet. The Amazon, though studied for centuries, remains a vast unknown. Even as forests vanish, the ancient stories they contain continue to unfold in silence. Rabbling himself described the discovery as a glimpse into evolution's workshop. In that workshop, time works slowly. Nature does not erase every prototype. Some survive, not as fossils, but as living witnesses to the deep past. Imagine holding that first specimen of Martialis under the microscope, seeing not just an insect, but a messenger from a world 120 million years gone. The soil from which it came was ordinary, dark, moist, full of roots and decay, yet in it lay one of the most remarkable time capsules ever unearthed. When the first humans appeared, Martialis was already ancient. When the continents drifted, when the dinosaurs vanished, when forests rose and fell, its lineage persisted. Unchanged, unseen, uncelebrated, until that moment of discovery, when light met eyes that could not see, and science met a creature that seemed to belong to another planet. In the years that followed, more specimens of Martialis were sought, but few were found. It remains one of the rarest insects known. Its scarcity makes it even more precious, not just to science, but to the imagination. It reminds us that the history of life is not confined to museums or bones. It breathes, it crawls, it hides. And sometimes it reveals itself in the most unassuming places, a scoop of soil, a flicker under a leaf, a whisper beneath our feet. The discovery of Martialis Heureka did more than fill a gap in the fossil record. It rewrote our understanding of what it means to be ancient. It showed that evolution's earliest chapters are not lost, only buried, and that even in the most explored places on Earth, there are still secrets older than time itself, waiting for patient hands and curious hearts to uncover them. In that single, fragile ant, the silence of 100 million years was broken. The first ant on Earth, or its closest living echo, had finally spoken. And through it, we learned that the story of life is not one of extinction and loss alone, but of endurance, quiet, persistent endurance, written in the soil of the world. When you first look at Martialis Heureka, it doesn't seem like much, a pale sliver of life, barely 2 millimeters long, fragile as dust. Yet in its delicate form lies a record of ancient innovation, a living diagram of how one of Earth's most successful creatures began. It is not beautiful in the way butterflies are, nor fierce like a predator. Its beauty lies in its strangeness, its silence. It is, quite literally, a ghost from the dawn of the ant lineage, an evolutionary whisper preserved not in amber, but in flesh. To understand Martialis, we must read its body as a text, each segment, each limb, a sentence written by time itself. The color of shadow. The first thing one notices about Martialis is its color, or rather, its lack of it. Its body is an eerie, milky white, almost translucent. It looks less like a creature and more like something half-forgotten by life. This pallor is the mark of its hidden world. In darkness, color is meaningless. Pigments serve no purpose when no light exists to reflect them. Over millions of years, Martialis lost the need for melanin or camouflage. Its world is one of tactile contact, not vision. The whiteness is not a deficiency, but an adaptation, a quiet surrender to eternal night. Like cave fish and blind salamanders, it has traded visibility for sensitivity. Its energy, its evolutionary investment, lies not in display, but in detection. Eyes that never were. Perhaps the most striking feature of Martialis Heureka is what it lacks: eyes. Look closely under the microscope and you will find smooth, unbroken exoskeleton where eyes should be. No lenses, no facets, no light receptors. Complete and deliberate blindness. This tells us something extraordinary about its history. Ants, descended from wasp-like ancestors, originally possessed excellent vision. They were hunters and flyers that tracked prey in daylight. For Martialis lineage to lose its eyes entirely, it must have abandoned the surface very early. So early, in fact, that sight became unnecessary before the diversification of most ant families. Blindness, here, is not a weakness. It is proof of antiquity. Proof of an evolutionary path that diverged into darkness while the rest of life still sought the sun. In its eyeless head, we see one of nature's paradoxes. Evolution sometimes advances by subtraction. The antennae, threads of perception. If Martialis cannot see, how does it navigate? The answer lies in its antennae, long, delicate filaments that curve and flick through the air like ghostly threads. They are not mere feelers, but instruments of astonishing sensitivity. Each antenna contains thousands of sensory receptors, tiny hair-like structures that can detect vibration, air currents, chemical trails, and even the faint electrical fields produced by other organisms. For Martialis, the world is not a visual panorama but a moving tapestry of scent and touch. It sees by chemical signature, mapping its environment through the invisible signals left by others. Every grain of soil, every passing insect, leaves behind a molecular fingerprint. Martialis reads these signatures as fluently as we read words on a page. It lives in a world of invisible messages, a sensory realm that is ancient, alien, and astonishingly precise. Mandibles, relics of a hunter. Then there are the mandibles, those curved, inward-facing jaws that resemble a pair of sickles. They are not the broad, muscular jaws of modern worker ants, designed for cutting leaves or carrying food. These are predatory tools, thin, sharp, surgical. They speak of a time when ants were solitary hunters, not social laborers. Under magnification, the edges of these mandibles glint like tiny blades. They are built for piercing and holding soft-bodied prey, perhaps larvae, mites, or other minute creatures of the soil. It's a glimpse into a forgotten ecology, one where early ants were more predator than builder, prowling the underground world as miniature hunters in a sea of roots. With these jaws, Martialis carries not just food, but history, the design of an ancient predator that never saw the light. The body, a creature between worlds. The body of Martialis tells another story, one of transition. Its form is elongated, slender, almost serpentine compared to modern ants. The waist, the narrow junction between thorax and abdomen, is distinct, but not as specialized as in later species. This suggests that Martialis sits near the base of the ant evolutionary tree, retaining primitive features that would later become more defined. Its exoskeleton is thin, smooth, and flexible, an adaptation for life in narrow tunnels. The legs are long and spindly, each tipped with claws for gripping loose soil. Every curve and contour of its body speaks to a life of movement through darkness, through spaces too tight for sunlight or air. If modern ants are architects, Martialis is a wanderer, a relic of an age before colonies, before empires. A heart without a queen. One of the most fascinating questions about Martialis is whether it lives socially or alone. Most modern ants are eusocial. They form colonies with queens, workers, and soldiers. But Martialis does not appear to follow that model. Specimens have only ever been found alone. No nests have been located, no queens observed, no evidence of organized caste systems recorded. This suggests that Martialis may represent a stage before full sociality, a time when ants were transitioning from solitary wasps into cooperative lineages. Imagine it, an ant that has no queen, no colony, no war, no kingdom, only the endless solitude of the soil. It is a window into evolution's workshop, a prototype for the empire that would one day follow. DNA, the ancient signature. Anatomy can tell part of the story, but it is in the genome that the deepest secrets reside. When scientists analyzed Martialis DNA, they were stunned. Its genetic lineage diverged from all other ants near the very base of the family tree, around 120 million years ago. To put that in perspective, when Martialis ancestors were crawling beneath the roots of Cretaceous trees, the world above was ruled by dinosaurs. Flowering plants were just beginning to appear. The Atlantic Ocean was still forming. Mammals were no larger than mice. In evolutionary terms, Martialis is as old as the soil itself. Its DNA confirmed what its anatomy had hinted, that this was not merely an odd ant, but the oldest surviving branch of the ant family tree. It is, quite literally, the closest thing we have to the first ant on Earth. The world through Martialis senses. Try to imagine life as Martialis experiences it. No light, no color, no sound as we know it. Instead, the world is vibration, humidity, scent. The earth around it hums faintly with life, the movement of worms, the pulse of roots, the rhythm of decay. Each vibration in the soil is a signal, each shift in temperature a map. In this quiet universe, Martialis moves with purpose, antennae waving, mandibles ready, every nerve tuned to the texture of the world. To us, it is alien. To it, this sensory darkness is perfection. It is not blind, it simply sees differently. Anatomy as time machine. Every inch of Martialis anatomy is a compromise between past and present, between what evolution once needed and what it still preserves. It is both ancient and modern, both primitive and specialized. Its blindness marks its age. Its mandibles recall its predatory past. Its solitary nature hints at the origins of ant society. Its DNA anchors it to the base of a tree that would one day branch into more than 14,000 species. If fossils are time machines made of stone, Martialis is a time machine made of life. The ghost that rewrites the map. Before Martialis Heureka, scientists had only theories about the first ants. After it, they had evidence. Its discovery forced a rethinking of ant evolution. That the earliest ants were not surface dwellers, but subterranean. That social behavior evolved after the move underground. That blindness, small size, and pale color were not degenerations, they were beginnings. In one fragile specimen, an entire evolutionary hypothesis found form. It was as if a missing word had been restored to the language of life, a word that changed the meaning of the entire sentence. The paradox of simplicity. There is a certain poetry in Martialis Heureka. It is the simplest of ants, yet the key to understanding them all. It lacks the strength, the organization, the numbers that make modern ants powerful. And yet, in its quiet existence, it embodies the resilience that defines its lineage. It survived not by conquest, but by invisibility. Not by domination, but by endurance. In an age of giants, it remained unseen, and that is how it endured when the giants perished. Martialis is proof that sometimes, the smallest creatures carry the longest histories. The legacy in silence. Today, Martialis Heureka is one of the rarest insects known to science. No colonies have been seen, no new populations discovered beyond a few precious specimens. It remains elusive, like the past it represents. But its existence changed everything. It gave shape to a mystery that had lingered since Darwin's time, the origin of social life among insects. Through its eyeless gaze, we can glimpse that long, dim corridor of time when life was learning how to cooperate, how to build, how to become more than the sum of its parts. Martialis stands at the threshold of that transformation, the first whisper before the chorus. In every way, it is an anomaly, a creature out of place, out of time. Yet that is what makes it precious. It bridges the living and the extinct, the surface and the subterranean, the solitary and the social. It is the ghost of an ancient idea, that unity, even in darkness, can become strength. And as long as the forests endure, and the soil remains alive, Martialis endures too, quietly, invisibly, writing its small, pale story beneath our feet. From the shadows of the soil emerged a quiet revolution, one that would eventually shape every ecosystem on Earth. The ancestors of Martialis Heureka, while remarkable as solitary beings, held the blueprint for something far greater. The first colonies, the first societies, the first cooperative empires beneath the surface of the planet. To understand the evolution of ant society, we must first step into the dim world beneath ancient forests, a realm where danger is constant, where survival requires more than strength or speed. The seed of cooperation. In the earliest ants, solitary life was a necessity. Life underground is unforgiving. Tunnels collapse, predators lurk, and food is scarce. Individual survival depends on efficiency, on cunning, and on instinct. But over time, natural selection began favoring individuals that shared resources, defended one another, and coordinated their efforts. This is the first spark of ant society. A single ant choosing, instinctively, to act for the good of others, not out of morality, but because it increased the chances of genetic survival. The result was a radical shift in strategy. From isolated hunters, ants began forming primitive groups, small clusters of kin that labored, explored, and protected together. Each generation reinforced the behavior. Cooperation became embedded in their DNA, encoded over millions of years. In evolutionary terms, this was monumental. The foundation of eusociality, the defining trait of all modern ants. Early nesting strategies. The first colonies were modest, hidden, and adaptable. Unlike the grand mounds or elaborate underground cities of modern ants, early nests were temporary shelters within leaf litter, rotting wood, or narrow soil cavities. These early homes served multiple purposes. Protection from predators such as spiders, beetles, or small mammals. Microclimate regulation. Soil retains moisture and buffers temperature changes, critical for survival in tropical Cretaceous forests. Resource consolidation. A central location allowed workers to share food and care for young more efficiently. In these humble beginnings, the blueprint for complex ant architecture was born. The first nests were simple, but they would eventually evolve into sprawling subterranean metropolises, complete with tunnels, chambers, and specialized zones for brood care and storage. Division of labor. The birth of castes. Cooperation alone is not enough for survival in challenging environments. To optimize efficiency, early ant societies began to specialize. Some individuals focused on foraging, exploring the soil for prey or organic matter. Others concentrated on nest maintenance, tunneling deeper or repairing damaged chambers. Still others guarded entrances, ready to fend off predators. These simple divisions of labor gradually became more pronounced, setting the stage for the caste system that defines modern ants. Workers, soldiers, and eventually queens each evolved specialized bodies and instincts for their roles. The genius of this system is subtle. It is not a conscious choice but an evolutionary outcome. Ants that cooperated and specialized survived. Those that did not were eliminated. Over millions of years, nature refined the system into the sophisticated social machines we recognize today. Communication, the language of pheromones. If the first ant societies were to function effectively, they required communication, a method to coordinate tasks, signal danger, and convey information about food sources. Enter the chemical language of ants, pheromones. Each ant produces and detects a complex array of chemicals, invisible to human eyes but profoundly effective in the soil. A worker might leave a faint trail leading to food, a warning of predators, or a mark to recruit assistance. Another might leave a pheromone to indicate the presence of a tunnel, a safe path, or a territory boundary. These chemical messages were the earliest form of ant language, a silent yet precise system that allowed coordination on a scale unimaginable for solitary insects. The first colonies were small, yet they functioned as cohesive units because each ant could interpret and respond to these signals with accuracy and consistency. Pheromones were the glue of society, the invisible thread linking individuals into a single, emergent organism. The rise of queens. In the early stages of ant social evolution, reproduction remained decentralized. Each female could lay eggs independently, and there was little difference between individuals. But over time, colonies that centralized reproduction around a single queen gained evolutionary advantage. With one individual responsible for laying eggs, the colony could allocate its workers entirely to other tasks: foraging, defense, nest maintenance, and brood care. This shift, the rise of the queen, was revolutionary. It allowed colonies to expand, to grow in size, and to outcompete less organized ants. In effect, it transformed the group from a collection of independent actors into a coordinated superorganism. The queen became the heart of the colony, the reproductive engine that ensured survival over generations. Workers became her limbs and eyes, the colony itself an extension of her genetic will. From solitary to superorganism. At this point in evolution, ants had begun a remarkable transformation. From solitary hunters like Martialis Heureka, they evolved into organized societies capable of division of labor, complex communication, and coordinated survival strategies. These early societies were the first true ant empires. They were small, hidden beneath the forest floor, yet they carried the seeds of domination. They perfected the art of survival through cooperation, preparing the lineage for global expansion after the Cretaceous extinction event. This is one of the most important lessons of ant evolution. Power does not always come from size, ferocity, or visibility. In ants, power comes from unity, specialization, and adaptability. Predation and resource management. Early colonies were not passive. They needed food to survive, yet their prey was elusive. Soil and leaf litter ecosystems are dense with tiny creatures, larvae, mites, springtails, and early ants became efficient hunters and scavengers. Workers coordinated hunting parties, using chemical trails to optimize foraging paths. Predatory efficiency increased colony survival, allowing more individuals to reach maturity and reproduce. Some colonies even began rudimentary farming behaviors, cultivating fungi in sheltered chambers, a practice that would later evolve into highly sophisticated fungus farming species in the tropics. Thus, even in the earliest stages, ant societies were more than a collection of insects. They were emerging ecosystems unto themselves. The lessons from ancient societies. The evolution of the first colonies demonstrates how natural selection can drive complexity from simplicity. From the humble, solitary Martialis to the first cooperative groups, ants discovered something that humans would only rediscover millions of years later. Organization amplifies survival. Through division of labor, communication, and centralized reproduction, these first colonies laid the groundwork for dominance over every terrestrial habitat. They showed that life could thrive not only by outcompeting others individually, but by building systems that allow the many to operate as one. A model for the future. By the end of the Cretaceous, ant societies had diversified, refined, and expanded. Colonies ranged in size from a few dozen individuals to hundreds, experimenting with strategies that would later define the Formicid world. Some remained subterranean, blind, and solitary like Martialis. Others ventured closer to the surface, developing vision, specialized mandibles, and social hierarchies. This experimentation created the template for the more than 14,000 ant species we see today, each tracing its ancestry back to those first cautious, cooperative gatherings beneath ancient forests. The first colony's legacy. The first ant colonies were fragile, temporary, and hidden from view. Yet in their quiet persistence lay the foundation for an empire that would span continents. Their story teaches us that greatness is not always visible, that survival often depends on cooperation rather than conquest, and that the smallest creatures can have the longest-lasting impact. From the soil beneath the Cretaceous forests to the leaf litter of the modern Amazon, the lineage of these first colonies endures. Martialis Heureka, with its solitary, eyeless existence, remains a reminder of the humble beginnings from which this empire arose, a ghost from which all ant society flows. The Cretaceous world was coming to an abrupt, catastrophic end. Above ground, the dinosaurs roamed forests and plains, enormous and imperious, their dominance seemingly unshakable. Flowering plants were spreading, insects buzzing, birds flitting. But the calm surface belied the gathering storm, a planetary-scale catastrophe that would forever alter life on Earth. Around 66 million years ago, an asteroid struck the Yucatan Peninsula. Its impact unleashed a chain of devastation unlike anything before or since. Firestorms, tsunamis, massive earthquakes, and a cloud of dust and debris that blotted out the sun for months. Temperatures plummeted, photosynthesis stalled, and ecosystems collapsed. The world above changed violently, and the reign of dinosaurs ended almost overnight. The challenge for underground life. For the inhabitants of the soil, the catastrophe presented a different challenge. While the surface world burned and froze, the subterranean realm offered shelter. Early ants, descendants of Martialis Heureka and other primitive lineages, had long been adapted to underground living. Their pale bodies, sensitive antennae, and soil-dwelling habits were not only survival traits in ordinary times but also a shield against extinction-level events. While large reptiles perished and forests withered, the soil remained a relatively stable refuge. Moist, insulated, and dark, it preserved pockets of life when the world above descended into chaos. Endurance through invisibility. The mass extinction demonstrated a remarkable principle. Invisibility can be survival. Small, hidden creatures like ants, insects, and some mammals endured because they were insulated from direct threats. Martialis and its close relatives did not need to see, run, or fight off gigantic predators. They did not rely on abundant sunlight, flowering plants, or open-air habitats. Their life had always been in darkness, a pre-adaptation that gave them resilience. The extinction event tested evolution's experiments, and ants passed with flying colors. Those that survived carried forward traits optimized for endurance, cooperation, and adaptability. In a sense, the very traits that had allowed early ants to thrive in soil, solitude, sensory precision, and cryptic living, became the keys to surviving Earth's most violent reset. Colony resilience. While individual ants were small, the collective power of colonies became apparent during this period. Colonies with division of labor, cooperative brood care, and efficient foraging had an evolutionary advantage. A solitary ant might perish during environmental upheaval, but a colony could buffer against disaster. Workers could redistribute resources, queens could continue reproducing, and underground tunnels offered stable microclimates. This emergent property, the resilience of the superorganism, allowed ants not only to survive but to set the stage for global dominance in the epochs that followed. The first colonies of ants were not just shelters for insects, they were life insurance policies encoded in behavior. Adaptation in the aftermath. After the initial cataclysm, ecosystems slowly recovered. Plants recolonized burned landscapes, insects diversified, and mammals began to rise. Ants, however, were already ahead. Their underground networks allowed them to exploit new resources faster than many other organisms. They were small, fast reproducing, and highly adaptable. Colonies expanded, branched, and diversified. Some moved closer to the surface, evolving vision, pigmentation, and more complex social behaviors. Others remained subterranean, preserving ancient traits. The post-extinction world was a canvas, and ants were ready painters, shaping ecosystems quietly, methodically, and with unparalleled efficiency. The evolutionary advantage of eusociality. The mass extinction also highlighted the evolutionary advantage of eusociality. Species that lived alone were more vulnerable to sudden environmental shifts. Those organized into cooperative societies, however, could endure disturbances that would wipe out solitary competitors. Division of labor allowed colonies to manage resources efficiently, coordinate responses to threats, and protect offspring. Queens ensured continuity. Workers ensured survival. The ant colony was more than a group. It was a resilient organism, capable of outlasting catastrophes. In this sense, the KPG extinction event served as a crucible, reinforcing the traits that would make ants some of the most successful animals on the planet. Emerging dominance. Following the extinction, ants rapidly diversified. Freed from competition with certain insects and small vertebrates, they began to explore new ecological niches. Some specialized as predators. Others scavenged or foraged for plant material. Some experimented with farming fungus in soil chambers. By the end of the Paleogene period, ants were no longer obscure soil dwellers. They had spread across continents, colonized forests, grasslands, and deserts, and developed sophisticated social systems that rivaled vertebrate intelligence in their complexity. The evolutionary spark that had begun in the soil of the Cretaceous now blazed across the Earth. The legacy of survival. The survival of ants through one of Earth's greatest catastrophes tells us much about resilience and adaptability. Traits that may seem minor, small size, soil-dwelling habits, cooperation, can determine survival over geological time. While the giants perished in fire and darkness, the small, persistent, and hidden survived, multiplied, and ultimately dominated. Martialis Heureka serves as a living testament to this principle. Its lineage endured while the world above transformed dramatically. Its descendants carried the lessons of survival into every ecosystem, shaping the course of life on Earth long after the dinosaurs' reign ended. A new world, a new opportunity. The post-extinction Earth was a world of opportunity. Forests regrew, new flowering plants appeared, insects diversified, and mammals began to explore niches previously closed to them. For ants, this was the moment to expand. Colonies grew larger, social structures more complex, and specialization flourished. New castes emerged. New behaviors evolved. New strategies for survival were perfected. And all of this was rooted in the quiet, patient adaptations of the earliest subterranean ants, the lineage of Martialis Heureka. What had begun in darkness beneath Cretaceous forests now radiated across continents, shaping ecosystems in ways both subtle and profound. The unseen architects of life. Today, ants are everywhere, from tropical rainforests to deserts, from mountains to cities. They shape soil, disperse seeds, and control populations of other insects. Their dominance is not due to size, strength, or speed. It is due to cooperation, organization, and resilience, traits honed in the soil over hundreds of millions of years. The KPG extinction, which wiped out the largest and most conspicuous life forms, only underscored the power of these traits. Ants survived, adapted, and thrived, becoming the hidden architects of the modern terrestrial world. In this sense, the first colonies of ants were not merely survivors. They were pioneers, shaping the trajectory of life for the next 66 million years. Endurance in silence. As the dinosaurs disappeared and mammals rose, ants quietly continued their work underground. Colonies expanded. Eusocial structures strengthened. Ecological influence grew. And through it all, the principles first demonstrated by Martialis Heureka, cooperation, subterranean adaptation, and resilience, continued to guide evolution. The mass extinction was not an end but a proving ground. Those ants that survived became the ancestors of every species we see today. They endured because they had already perfected the art of survival in darkness. Their story is a reminder. Sometimes, the quietest, most hidden life carries the longest history, shaping the world in ways we rarely see. After surviving the cataclysm that ended the age of dinosaurs, ants entered a new era, an era of expansion, diversification, and transformation. The soil-dwelling descendants of Martialis Heureka now faced a planet filled with opportunity. Forests regrew, climates shifted, and ecological niches, once monopolized by reptiles and other ancient lineages, lay open. The stage was set for one of the most remarkable evolutionary radiations in the history of life. Emergence into the light. While their ancestors thrived underground, some lineages of ants began venturing closer to the surface. The advantages were immense. Access to new food sources, from seeds and nectar to other insects, and the ability to explore above-ground niches previously unavailable. With this move came evolutionary pressures, improved vision, pigmentation for camouflage, and specialized mandibles for new diets. The transition was gradual but transformative. From shadow dwellers, ants became architects of both soil and surface ecosystems. Their colonies grew larger, social organization became more complex, and new behaviors emerged, some as sophisticated as farming and warfare. Global colonization. Ants are now found on every continent except Antarctica. This global spread has deep roots in the post-Cretaceous period. Continental drift played a significant role. As the remnants of Gondwana and Laurasia drifted apart, ants rode the shifting continents, colonizing new lands. Island chains became stepping stones for further expansion. Climatic variation spurred specialization. Tropical rainforests nurtured diverse, colorful species. Grasslands favored fast-moving, aggressive colonies. Deserts selected for survival strategies that minimized water loss and maximized cooperation. Within a few tens of millions of years, ants had radiated into virtually every terrestrial ecosystem, a feat matched by very few animal groups. Diversification and adaptation. The diversification of ants following the KPG extinction is staggering. From a handful of primitive lineages, tens of thousands of species emerged, each adapted to its environment. Army ants, nomadic predators, striking in coordinated swarms. Leaf-cutter ants, masters of agriculture, cultivating fungus for sustenance. Weaver ants, architects of arboreal nests, weaving leaves with silk produced by larvae. Trapjaw ants, rapid, lethal mandibles optimized for predation. All of these diverse forms trace their lineage back to the subterranean, eyeless ants like Martialis, which first mastered survival underground. This evolutionary radiation demonstrates the power of early adaptations, cooperation, division of labor, and subterranean efficiency. These traits provided a foundation that allowed ants to exploit new niches with astonishing speed. Ecosystem engineers. As ants spread, they began to shape the very world around them. They are ecosystem engineers, influencing soil structure, nutrient cycling, and plant dispersal. By tunneling and aerating the soil, they improve water penetration and root growth. By dispersing seeds, they influence plant community composition. By preying on insects and other invertebrates, they maintain population balance. Ants are small, yet their collective impact is immense. They are among the most influential creatures on land, shaping habitats in ways that mammals and birds never could. The humble colonies that survived the mass extinction had become architects of global ecosystems. The role of climate. Climate played a major role in ant radiation. Tropical forests, warm and stable, became cradles of diversity. These forests preserve complex leaf litter habitats, perfect for colonies to establish. Meanwhile, temperate zones saw fluctuations in species composition, forcing ants to evolve strategies for seasonal survival. Cold-adapted ants developed hibernation behaviors and nesting strategies that buffered against frost and scarcity. Deserts imposed extremes of heat and aridity, selecting for behavioral innovation. Nocturnal activity, water-efficient physiology, and highly cooperative foraging. Through climate-driven adaptation, ants became a model for resilience, able to occupy nearly every niche in terrestrial ecosystems. The evolution of specialization. Ants did not merely spread, they specialized. Different lineages exploited unique food sources, habitats, and behaviors. Some became seed harvesters, shaping vegetation patterns. Others evolved predatory efficiency, controlling insect populations. Some cultivated symbiotic relationships with plants and fungi, a form of agriculture unseen elsewhere in the animal kingdom. These innovations illustrate a key principle of evolution. Early success enables later experimentation. The cooperative foundation established in the first colonies allowed ants to explore new ecological strategies without jeopardizing survival. Competition and cooperation. While ants expanded, they also encountered competitors: termites, beetles, and other social insects. The evolutionary arms race encouraged further specialization. Larger colonies with soldiers dominated resource-rich areas. Chemical communication systems became more sophisticated, improving coordination and foraging efficiency. Defensive strategies, such as stings, venom, and chemical deterrents, evolved to fend off rivals. Yet ants maintained a balance between competition and cooperation, both within and between species. Their social systems allowed them to thrive even under ecological pressure, a testament to the power of eusociality. The importance of social innovation. The key to ant success is not size or strength, but society itself. Cooperative brood care ensures high survival rates for offspring. Division of labor maximizes efficiency. Communication systems coordinate complex behaviors across thousands or millions of individuals. Social innovation allowed ants to occupy habitats and roles that solitary insects could never conquer. It is the defining factor behind their radiation and dominance. Even in extreme environments, deserts, mountaintops, rainforests, ants adapted through social ingenuity rather than individual prowess. Legacy of Martialis lineage. The radiation of ants after the mass extinction demonstrates the enduring influence of Martialis Heureka's lineage. Its subterranean, blind adaptations provided resilience. Its solitary efficiency formed the basis for social evolution. Its genetic heritage allowed rapid diversification in a changing world. In essence, the first ant survival strategies became the blueprint for global dominance. The quiet ghost from the Amazon was not merely a curiosity, it was the progenitor of a planetary empire. The modern implications. Today, ants number more than 14,000 species and represent a significant portion of terrestrial biomass. They are ubiquitous, influential, and often invisible in daily life, yet they continue to shape ecosystems profoundly. Rainforest floors teem with their colonies. Grasslands are dotted with nests and foraging trails. Deserts harbor nocturnal ants thriving in extreme conditions. This global spread is the result of an evolutionary story that began 120 million years ago, with small, blind, subterranean ants like Martialis Heureka, survivors of extinction, innovators of society, pioneers of global colonization. The grand narrative. The radiation of ants teaches us a broader lesson about life on Earth. Success is rarely about brute force. It is about resilience, cooperation, adaptability, and the capacity to innovate under pressure. From shadowy beginnings in Cretaceous soils to the complex ecosystems of today, ants exemplify how life thrives through collective action, social intelligence, and persistence. The story of ant radiation is, in essence, a story of life itself, a testament to the hidden architects who quietly shape our world. Life in the shadowy soil of the ancient Amazon gave ants a survival advantage, but as descendants of Martialis Heureka ventured into the light, evolution began to experiment. Some ants remained blind and subterranean. Others developed eyes, pigmentation, and sensory adaptations that allowed them to explore new niches above ground. This chapter is the story of these evolutionary experiments, how ants diversified their senses and forms to thrive in environments that were once unreachable. The re-emergence of vision. For millions of years, subterranean ants like Martialis had thrived in darkness. Their antennae served as eyes, and their pale bodies reflected the absence of light. But when ant lineages emerged from the soil, a new challenge arose. The surface world was no longer invisible. Vision became essential. Above-ground life demanded the ability to detect predators, locate prey, and navigate complex landscapes. Over generations, eyes reappeared in some lineages. Compound eyes developed with varying degrees of complexity. Large, acute eyes in predatory species such as tiger ants, allowing them to hunt with precision. Moderate eyes in generalist foragers, balancing light detection with other senses. Minimal or absent eyes in species that returned to soil or lived under dense forest canopy. These variations reflect the adaptive experimentation of evolution. Each species found a sensory strategy best suited to its ecological niche. Pigmentation and camouflage. Alongside vision, pigmentation re-emerged in surface-dwelling ants. Coloration was no longer unnecessary. It became critical for survival. Camouflage. Brown, black, or red bodies blended with soil, bark, and leaves, reducing predation. Warning colors. Brightly colored species, often associated with venomous stings, signaled danger to potential predators. Temperature regulation. Pigments influenced heat absorption, helping species survive in hot environments. Some ants remained pale, retaining ancestral traits in dark soil or subterranean habitats. Others evolved striking patterns, each reflecting an ecological experiment in adaptation. Mandibles and specialization. The mandibles of surface-dwelling ants also evolved dramatically. While Martialis had simple, curved mandibles for hunting soft-bodied prey underground, new lineages diversified into highly specialized tools. Trapjaw ants, mandibles that snap shut at incredible speeds to catch prey. Leafcutter ants, broad, sharp mandibles for cutting and processing vegetation. Predatory ants, long, serrated mandibles designed to immobilize struggling prey. These adaptations were not mere modifications. They represented a fundamental shift in ecological strategy. Ants could now exploit resources inaccessible to their subterranean ancestors. Sensory integration. The evolution of vision and pigmentation did not eliminate the importance of other senses. Antennae remained critical for chemical communication, pheromones, detecting vibrations in soil or leaf litter, coordinating complex colony behaviors. This integration of multiple sensory modalities, combining old subterranean tools with new surface adaptations, allowed ants to excel in diverse habitats. Evolution was layering new abilities atop ancient ones, producing species uniquely tuned to their environments. The experiment of light and darkness. Evolutionary experiments were not uniform. Some ants ventured into daylight but retained ancestral traits, creating a hybrid lifestyle, foraging in leaf litter or under vegetation while still relying heavily on tactile and chemical senses. Others fully embraced surface life, developing bright coloration, acute vision, and aggressive predation strategies. This spectrum of adaptations illustrates evolution's trial-and-error approach. Multiple strategies were tested, refined, and sometimes discarded. The result is the astonishing diversity we see today, from the eyeless subterranean specialists to the brightly colored, visually acute hunters of the forest canopy. Case study. Army ants. Army ants are a remarkable example of evolutionary experimentation. While some lineages retained underground adaptations, army ants developed large, functional eyes to navigate above-ground foraging raids, coordinated group hunting strategies using chemical trails, specialized castes for offense, defense, and brood care. Their success is a testament to how surface adaptations, layered upon the foundational traits of Martialis lineage, can produce highly efficient social organisms. Army ants are both ancient and modern. They preserve ancestral behaviors like cooperative hunting while exploiting new sensory tools to dominate their ecological niches. The role of habitat diversity. Habitat diversity drove evolutionary experimentation. Ants that moved into deserts, grasslands, mountains, or temperate forests faced distinct pressures. Desert ants evolved reflective exoskeletons and efficient water conservation. Forest ants optimized camouflage and navigation among complex vegetation. Mountain ants developed resistance to temperature fluctuations and reduced metabolic rates. In every case, sensory and structural adaptations reflected the interplay of ancestral traits with environmental opportunity. Evolution was testing new ways to survive while retaining the lessons learned underground. Behavioral innovation. Alongside physical adaptations, behavior evolved in parallel. Vision and pigmentation enabled complex foraging patterns, territorial defense, and predator avoidance. Ants experimented with nighttime activity patterns in desert and forest species. Complex foraging trails guided by both visual and chemical cues. Nest architecture adapted to light exposure, humidity, and temperature. Behavioral innovation, coupled with sensory experimentation, allowed ants to colonize nearly every ecosystem on Earth. Genetic evidence of experimentation. Modern genetic studies reveal multiple independent reemergences of vision and pigmentation across ant lineages. These events are not uniform but represent repeated evolutionary experiments in response to environmental pressures. Each experiment was guided by survival, trial, and error. Some succeeded, creating thriving surface-dwelling species. Others failed, returning to subterranean life or disappearing entirely. The continuity of ancestral traits. Despite these experiments, ancestral traits persist. Antennae remain exquisitely sensitive. Social cooperation remains paramount. Mandibles retain versatility, even when specialized. The evolutionary narrative of ants is thus a layering process. Ancient adaptations form the foundation, and new traits are added through environmental experimentation. A window into evolution. Studying these evolutionary experiments provides insight into how life adapts to new opportunities. Ants are both conservative and innovative. They preserve ancient strategies while continually testing new forms and behaviors. Martialis Heureka exemplifies the conservative end, subterranean, eyeless, and solitary, while its descendants represent the innovative spectrum, from leafcutter engineers to visually acute hunters. The diversity of sensory and structural adaptations in ants is a living record of evolution's flexibility, patience, and creativity. Lessons from the darkness and the light. From the soil-dwelling shadows of the Cretaceous to the sunlit canopies of the modern world, ants demonstrate a powerful evolutionary principle. Adaptation is not linear. It is experimental, iterative, and context-dependent. Traits that are beneficial in one environment may be unnecessary in another, yet evolution preserves the capacity to experiment, to innovate, and to succeed. In the story of ants, we see a continuum, from the ghostly Martialis in darkness to the dazzling diversity of modern species. Evolution experiments, refines, discards, and repeats, and ants are its enduring laboratory.